Hi, we're starting over. This is a retake. Um, uh, we learned about Hess's law. Congratulations, we're doing practice problems. Okay, so next problem, Rainier, what did you do for the second reaction?
I multiplied it by -0.5.
Minus, so you flipped it and then halved it. Okay, let's flip it and then halve it. So it's CO goes to 1C, so I'm not even gonna write this, the 1, plus a half O2. So I'm going to multiply by negative a half. Okay, third one, what'd you do? You flipped it for sure.
Yeah, flipped it.
Did you have or do anything multiplication? Okay, let's just flip it. Okay, last one.
Multiplied it.
Multiplied it by 1?
There's nothing. Yeah.
Nothing. Okay.
Well, it's not what Malcolm said. That's exactly what I said to do. That's too routine.
No, but it didn't. Why didn't it work when I was writing it out?
I told you to flip no, you did flip it.
I did flip it. That's what I'm saying, man. Okay. Times 1. Okay. Now let's see if everything cancels. 3H2, we want that. Let's highlight it. We get what we want, 3H2. We get CH4, what we want. We get 1H2O, which is what we want. And we get 1CO, which is what we want. So now let's make sure everything else cancels out. 3 halves H2, 3 halves O2. You have 2O2 on the reactant side. We don't want that. Our CO2s cancel for sure, Z's. And our carbons cancel for sure, Z's.
Your oxygens cancel too.
Whoa, because I'm an idiot and I wrote.
3 halves plus 1 half equals 2. Yeah, because we have 2.502 on the right and 2.502 on the left.
No, we don't.
No, we do. We have 1.502 in the first equation on the left and 102 in the first equation on the left, or sorry, in the fourth equation on the left. And on the right side, for the second equation, we have half O2, and for the third equation on the right side, we have 2 O2.
Beautiful. Okay. Good. Okay, good. Guys, guess what my eyes didn't see? I did not even see this over here. Okay, it was merged. Okay, perfect. Good job, guys. We did it. Look at that. Okay, really good. Just give me, I'm kind of blind. Okay, now we have what we want. Excellent. Okay, good job, guys. So we get the net that we want, 3H2 plus CO plus CH4. And low-key, I think I remember this is what happened last time. I couldn't find my 2O2. Okay, CH4 goes to CH4 and H2O. And what you would do is you'd multiply all of the manipulations that you did algebraically. So what did you get for your H of reaction? Okay. Good job, guys. That's just because it's specifically a combustion reaction. So it's not about, sometimes we just name special subsets of reactions. No. Okay, what did we get? Sam?
What did we get? For what?
You can read off of Malcolm's. Just put down the telescope.
I haven't checked it. So 394.3.
Positive 94.3?
Yes. 390.
Kilojoules per mole of reaction. Wowza.
Okay, so that's definitely not right.
That's definitely not right.
Hold on, I forgot a 4. Is it negative 205? Negative 205.7. Yeah.
Okay.
I used a 4.
Good job, guys. What a way to persevere. Okay.
Questions on the SP this hard?
I don't know. It's up to them. So next one should have been much easier. Next one should have been much easier. So, okay, for the second one, you do the same process of algebraic summation, but you had way less reactions to work with. So, Nora, what did you do for the second one?
Like, oh, not the first equation, not the second. Okay.
Practice problem, this one.
Number two, the first one. Okay,
Yep.
I got a little, okay, I think I multiplied the first equation by 2.
Okay, and did you keep it on the same order?
It looks like I did.
Okay, so you multiplied by 2, giving me 1N2 plus O2 goes to 2NO, which means I would have multiplied my heat of formation times 2. Then what did you do for the second equation?
I believe I flipped it.
You should have flipped and
doubled it.
doubled it. So it becomes 2NOCl goes to 2NO plus Cl2. And that would mean I'd have to flip and double my heat of formation value with that equation. And I would have gotten my net much easier. This is probably more like what the AP is going to give you.
Do we
Okay.
not have to flip and double the first reaction as well?
If you, oh, you would also have to flip it.
Well, yeah.
So become times -2. So let's flip.
Wait, why are we flipping the first reaction?
Because it doesn't work. The NO, N2 is on the wrong side. Okay, so that means now you should get that your NOs cancel. And now you have what you want. You have 2NOCl goes to N2 plus O2 plus Cl2. So then what was your heat of formation value if you flipped and doubled both reactions? What would the sum be of flipping and doubling both reactions and then adding them together? Why would you need to divide? You don't want to divide it. Just give me, you can't divide it. It's this is the, okay. Got it. Do we have anyone that has it? Kilojoules per mole of reaction or for this whole reaction. Okay, good. Okay, next one. We're asked, what is the total? Okay, so do we really want to go over these next two? Okay, cool. So let me just quickly check where we have to go. Ew. Okay. Sounds good. I'm only gonna do one. Okay, and then the last one will be your responsibility. Okay, because I want to move on to the other two ways that we can calculate. All right, and they're a little faster. Well, one's faster, one's slower. So, this one, what we're gonna want to do is for H2, Cl2, 2HCl, we are going to want to keep it the same. Okay, I don't see us needing to flip it. For the second one, okay, so I'm just gonna write it separately so it's just easier to see. And I'm just gonna keep HF normal to itself. For the second one, I'm also gonna keep, okay, this. So I'm gonna keep it same because the C2H4 that's found in the net is also on the reactant side in a ratio of 1. So I'm gonna just keep it HF. And then for the last one, I'm going to flip it because I want my C2H5Cl to cancel out and I want to end with C2H3Cl with a ratio of 1. So I'm just going to flip it. So it becomes C2H5Cl goes to C2H3Cl plus H2. So it's gonna become negative H of F. And that should get me, when I sum them up, I cancel out my cancel out this HCl, leaving me with one HCl, which is what I want. I cancel out my C2H5Cl, and I cancel out my H2. And that gives me the net sum of Cl2 plus C2H4 goes to HCl on product, one of them, plus C2H3Cl, which is what I wanted. So then my HF, okay, would be equal to HF plus HF. Oh God, I just spit. That was gross. Negative 184.6 minus 65 plus 138.9. Can someone do that for me? Yes.
How did this reaction happen? Because it feels like the reactions are kind of circular. Because to make HCl, you need to have HCl to make
So
HCl.
technically, these reactions aren't happening. These aren't actually happening. What we're saying is we did some reaction, and I want to figure out how much energy this reaction took. Well, if I can figure out through mathematical manipulation what a series of reactions, if put together with known energies, that could composite make this reaction, not necessarily in lab. They don't actually make it. Like, this is not a lab that you do. You don't actually mix these three reactions. What you're doing is you're just using these three reactions to figure out the energy that would go with your specific reaction. But this is not translating into lab. Like, you would not do these three reactions in the same pot together. They would not work.
Okay.
You're just using the numbers. That's a great clarification. Thank you for asking that. Okay. All right. So I'm going to leave the last one. Did the last two make sense? Last two. Okay. Let's move on to the second way we can use it, which is actually much easier. It takes all of this Hess's law thing where we're looking for our products, we're looking for our reactants, and we're trying to cancel out, and it just minimizes it to the following. Given a table of information, the H of a system is equal to the sum of the products, individual product species times their molar coefficient, minus the sum of the individual reactant species, enthalpy, times their coefficient. And it gets rid of all the algebraic summation. It just takes care of that because it gives you a tabular data for individual chemical species. So you just make it on your own instead of having to use a bunch of equations. The AP will ask you to know both, plus the third one I'm going to teach you. So, for example, okay, CH4 plus 2O2 goes to CO2 plus 2H2O. The enthalpy of this system will equal the sum, okay, and maybe I'm just going to write brackets. The sum of whatever the enthalpy of CO2 is, plus the enthalpy times 2 of H2O, minus the enthalpy of CH4, plus the enthalpy of 2 O2s. And so what we do is we look down at this table and we say, well, CO2 requires the following amount of energy to form. CO2 is negative 393.5 plus 2 times how much energy does it take to form H2O? And let's choose, we're going to choose, let's see, what did I choose last year? I chose H2O liquid. So let's do H2O liquid, negative 285.8. Negative 285.8. Minus my product energy is required to form the individual species of my product. So, I didn't write this small enough. Okay, CH4 is gas, negative 74.9 plus 2 times, well, O2 is a diatomic element. It's in its natural state. So we would say times 0. And what you get then is you get everything that Hess's law would give you, but in a more basic equation. And it becomes H of the system equals negative 891 kilojoules per mole of reaction. So what the connection is that it gives us the same value without the hassle. The AP again expects you to know both. Yes. N is the molar ratio. Yeah, N where N equals the molar ratio.
Is this one of those things you said like it really isn't tested on, or was that another thing?
No, that was another thing. This is definitely tested on. This is a very common MCQ actually. Yes.
Do we have to, would that chart be given to us?
Yes, the data, the individual necessary data would be given to you, but notice they might not give you O2 because they assume that you recognize that O2 is 0. Same with the pure metal. If it was like a pure metal like silicon S, it would be 0. Solid. Silicon in its solid state is its natural state under standard state conditions, making it 0. Yes.
So it's like the end, the number of moles
The coefficients. It's replacing what the manipulations that you would do if you multiply. So it's actually ends up being the coefficients. Yeah, it's your molar ratio, your coefficients. And I can write that even more clearly. Your coefficients.
Oh, and it's the mole.
Yeah.
Nothing.
Yeah. So this is a much easier way to do what you just learned above, but I have to teach you both because you're tested on both.
Well, how would we?
They would give you what you need.
Yeah.
So try the practice problem below, and then I'll teach you the third way. So for this problem, you're going to set it up the same way where you look, you're now not using algebraic summation. Now we're skipping all of that and just saying, well, as long as I know how much energy it took to make the individual species, I can just add up my product energies and subtract my reactant energies. Okay. So you should have placed your original equation to have your 2 SO3 energy requirements to make the 2 SO3 molecules, subtract from it the 2 SO2 molecules plus the O2 molecule. Notice, these are all standard state conditions, right? So you should have gone that SO3, and I'll put it in another color. SO3 is negative 396 times 2 minus 2 SO2. Okay, minus 2 times negative 296.8 plus, what's the heat of formation for a diatomic element that's in its natural state? 0. So what did you get for your total, guys? One more time. Thank you. 198.4 kilojoules. Would it be negative? It's negative times a negative, right? So it's a positive.
Well, it's negative 600. It's like negative 750 something minus plus. It's negative.
It's negative.
It's overall negative.
Is it negative 198.4? I don't have a calculator. Okay.
It's like negative 800 plus.
Yeah, it can be. Sorry.
600. Yeah, negative 800 plus 600.
Okay, perfect. So the third type of way, sounds good. The third type of way is an approximation. Yes, these are more exact. These are 2 more exact ways because they're the same rendition of each other. Yes. Why is the enthalpy varying across states? Because remember, different states of matter require different energy input to be in that state of matter. The enthalpy is the heat of the system to make these chemical species. No. Not at all. Excellent. Malcolm, what are you doing? Malcolm, don't threaten people with a chair. Okay, so that's going on record. Okay, so the final way, bond energy calculation to calculate enthalpy is an approximation method. It is the least precise out of all of these. But conceptually, it's the most precise. Numerically, the least precise, but conceptually, the most precise, because what this has us look at is looking at the energy required input to break the bonds, subtracted by the energy released to make the new bonds, which is actually what's happening when you think about the rearrangement of a reaction. But the numbers just aren't as precise because of our measuring tools. Okay?
Hypothetically got better measuring tools, would be more precise.
It's just conceptually more precise, but you would hope that yes, yes, yes. So what we depend on is the structural formula, and i.e. the structural formula are your Lewis structures. The structural formulas show us the bonds broken versus bonds formed, or the bond rearrangement. That's maybe a better way to put it. The bond rearrangement in a chemical reaction or a chemical process. So you already know, okay, prior knowledge, that when we break bonds, okay, it's an input of energy. Input energy. Okay? And when we make bonds, it's in a release. We also know prior that bond energy increases with shorter bonds. So bond energy increases from single, greater for double, highest for triple. Because bond energy is an indication of how strong that bond is. It's the energy required to break the bond. Okay, so finally, we also already know that kind of goes with it, that the shorter the bond, right? The stronger the bond, the greater the bond energy, which kind of connects to the point above, right? So what we do here is we do a similar process, but now instead of doing H formation, we now calculate this based off of bond energy. Sagarika? So again, it's tabularized data. And so what we say is that our equation is that the sum, okay, of our molar ratio amount, our stoichiometric amount of bonds broken, minus the sum of our stoichiometric amount of bonds formed. And we identify each type of bond broken and each type of bond formed. And we just do the algebra with it. So, please note, this is an approximation of H of the system. Even though conceptually it's actually more accurate. Yes.
Where does that error stem from?
We just have a really hard, we have to use programs to generate relatively accurate estimations of bond energy, but we can't actually measure bond energy.
Oh, okay.
It's very, yeah, it's near impossible in lab. So we use computer generation.
Okay.
And the programs are really correct. Like they're really close. You won't see a huge variance, you'll just see a slight variance in answers. Yes.
Wait, so this is the representation of enthalpy.
Yes, this is representation of enthalpy
So
via bond energy calculation.
what exactly is the difference between the two representations? Because it seems to me like,
One is more accurate than the other numerically.
but from a conceptual standpoint, isn't this one representing enthalpy on a different?
No, not necessarily, because the energy, heat energy is held in those bonds. So when you break and rearrange, you are releasing and creating a transfer of heat energy. That's actually where your heat energy comes from. Your chemical enthalpy energy is stemmed from the bond rearrangements.
So then how exactly can you get negative energy? Is that just
Because it's energy release overall. We get more, the new bonds formed as a product are more stabilized than the prior arrangement. So you send energy out into the universe, out of the system. The energy still technically exists. It's just not in your chemical arrangement anymore. It's now out to the system. But energy is still conserved in the universe, the system plus the surroundings. Yes. So what we would do for this one is a lot of times you need to actually draw out the Lewis structure to understand. So what you have is CH4. Okay. Bonding with two O2s that are double bonded. Going to CO2, which is a double bond to a C. Going to H2O. Okay, and you're gonna want to make note of the coefficients. They matter. So what we would say is bonds broken. Oh, bonds broken wise. What got broke? So I broke, okay? I'm gonna break 4 CH bonds and 1 double O bond. But technically, I'm actually not breaking 1 double O bond, I'm breaking 2 double O bonds. So what I would say is I broke 4 CH bonds and 2 double O bonds. And I make, in a different color, I make 2 CO bonds double bonded and 2 OH bonds, but not just 2 actually. Technically, it's 2 times 2. So it's 4 because of my molar ratio. So I make 2 C double O bonds and I make 4 OH bonds. And now I do my math and I say, okay, so my enthalpy is going to equal my bonds broken minus my bonds formed times their molar ratios or their relative stoichiometry. So I would say bonds broken, 4 CH bonds plus 2 double O bonds values. Okay, that's my bonds broken minus my bonds formed, which is 2 CO values and 4 OH bond making values. And notice this time it's not product minus reactant. It doesn't, we don't flip our arrangement for this estimation. Okay, so then what I get is that this would equal 4 times, according to my table, we have CH bonds, we have double O bond down here, we have C double O bond, and this particularly is C double O in, oh God, in hold on. C double O bond in carbon dioxide, which
Would you be making 4 CO bonds?
no, because I only have 1 molar ratio.
You only have one CO2.
I only have 1 CO2.
Oh, yeah.
And I'm also making let's see, 4 OH bonds. So what my math becomes then is it becomes 4 times CH, which is 410, plus 2 times double bonded O, 498. All that together, yeah, for sure. Minus 2 times CO, which is 732, plus 4 times OH, which is 460. Okay. And can anyone do that math to get me the proper value? Yeah, of course. No, it's okay. It's okay. Don't feel bad. Yeah.
Why exactly do we flip around the other one, but not this?
Because if you think about it, you're trying to figure out if your enthalpy is negative or positive, right? So if you have an input of energy that's always a positive value for enthalpy, bonds broken, you're inputting energy, minus your bonds formed, which is always going to be a release of energy. So you're going to want to subtract and see if it took more energy, endothermic, to break your bonds than it did in releasing energy, represented by the opposite perspective of how much energy is stored in your new bonds. So that way, mathematically, if your bonds broken value is greater than your bonds form value, it would represent an endothermic reaction where it took more energy to break the bonds than it did in making the new bonds. Okay? That's why.
I can get past stems from the fact that both of them seem to be representations of energy before and after.
Yes.
How exactly is the other one like? Wouldn't that also apply to the other situation as well, where you have?
Bonds formed minus bonds broken?
I guess so. Yeah, when you have energy
No.
before, energy after, and then that's the same as bonds formed.
No. It would create the opposite meaning of enthalpy. So when you get a negative, it would really if you did the math, it won't mean the same thing. You'll get a number opposite of what you should. Huh? Is that 732?
Yeah, why is this 732?
Because it's the CO bond.
Isn't it not 350? I'm moving to 350.
CO is 700.
700 700.
Sorry, 001.
Yeah. So does anyone know this math?
2012.
Negative 668. Yep. Negative 668 kilojoules per mole of reaction. So try this next problem using the table, and you're gonna have to draw the Lewis structures. Okay, last one, what you have is N2, which is a triple bond. Reacts with 3H2, which is a single bond. Okay, to produce 2NHH. Oh, sorry, H. Okay, and I'm ignoring lone pairs because they don't matter to me for this. So what I'd say is bonds broken. I break, okay, a triple bonded N, and I break 3 H single bonds. So 1 triple bonded N and 3 H single bonds. And I make three NH bonds. 3 times 2 NH bonds. So I make 6 NH bonds because I have 3 bonds of NH in 1 mole of it, and I have 2 moles of NH3. So then I do my matharuni, and I say that the H of the system is equal to the sum of my bonds broken, which is N triple bonded, plus 3 single bonded H, minus bonds formed, which is 6 NH. And I should have gone for my values that triple bonded. I'll make this in a green. Triple bonded N, single bonded HH, and single bonded NH. So 945 plus 3 times 436 minus 6 times 390. And what did you get for your total approximation? Total approximation. Negative 87?
Yeah.
Okay, Negative 87 kilojoules per mole of reaction. Oakley dokley artichoke. So I'm gonna stop there for today. We're gonna warm up with problems 2 and 3 on Monday. And you have an AP problem video and an intro to heat transfer, which is about 12-15 minutes for Monday or the next class, depending on what year you are.